hear me?
Yeah, perfect.
Okay. So today we're going to learn about the hexagon and why it's considered one of the most important shapes in the universe, and why I also think it's a pretty cool shape. So many would think that the triangle or the circle would be the most common shapes in nature because of structural integrity or because it's very circular and there's a lot of circular parts in nature. But in reality, it's actually the hexagon, which is the most common shape structure that you can see on the planet. So here's some pictures of areas where you can see the hexagon. So the snowflake makes like a hexagon type of shape. The turtle shells have hexagon-like shapes as well. So it's pretty interesting where the hexagons are seen. So here's today's agenda. I'll be skimming through this part because I think it'll take a bit long. So we'll first talk about a quick reminder between a regular hexagon and an irregular hexagon. So when I talk about a regular hexagon, it has to be in 6 equal sides and 6 angles with 120 degrees. It has to be a closed shape as well and 2-dimensional. So what makes these properties particularly interesting is that due to the configuration of the 6 sides and the angles of the 120 degrees, the hexagon shape actually best fills a plane with equal sized units and leaves no wasted space. As a result, what you can see on the right is a tessellation. Basically, in plain terms, tessellations are repeating patterns of flat shapes that have no overlap. So why do we think that tessellations are really important? It's because tessellation patterns are seen everywhere in nature. For example, here's an up-close picture of snakeskin. Here, this is a tessellation as well because there's a repeating pattern of a flat shape. Also, it allows no gaps between any of the cells, and this prevents any bacteria or anything to bypass through the skin into the internal systems, which is why tessellations are really important for covering anything. So this concept of tessellations can also be applied to honeycombs. What we can see here are hexagonal tessellations in the middle. These hexagons are really important shapes for the bees as they can structurally hold the queen bee's eggs and store the pollen and honey the worker bees bring to the hive. When you think about it, making circular cells wouldn't work too well because it would leave gaps between the cells and it would be weak structurally. However, bees could also create triangular tessellations or square tessellations because they don't allow any gaps in between. Why is it that hexagons are specifically used by bees? And this brings the honeycomb conjecture or the honeycomb theorem because it has been proved. So in ancient times, there was a Roman scholar named Marcus Terentius Varro who had a collection of pet bees, and he observed them for many years and proposed that hexagonal structures that honeybees have or build are more compact than any other shape. It was only thousands of years later that Thomas Hale, a mathematician at the University of Michigan, was able to prove it through a mathematical proof, which is called the honeycomb conjecture. Basically, the honeycomb conjecture proves that hexagonal tessellations allow for the most efficient way to maximize area while having minimal perimeter than any other shape. So at the top, we see a formula of the honeycomb conjecture, and it's pretty complicated, but it essentially proves that in the bottom. So on the left side, we see a hexagon, a regular hexagon, and an equilateral triangle. So the equilateral triangle and the hexagon have 6 units as its perimeter, which is noted by the numbers. However, if you noticed on the left side, the hexagon is made out of 6 smaller equilateral triangles, while the triangle on the right is made out of 4 equilateral triangles. What this proves is that the hexagon is more compact than the triangle because it's able to fit in more area in the same amount of perimeter. On the right side, we can also see the same thing because they have the same amount of area, which is 16 centimeters cubed. However, the perimeter of the square is 16 centimeters, while the perimeter of the hexagon is less. So what I'm going to do here is create a application example. So let's take a typical honeycomb, which is a honeycomb cell, which has an area about 23.4 millimeters cubed. And if we take an area of a 10 by 10 honeycomb, a centimeter honeycomb, which would be 100 centimeter cubed, then divided by 23.4 millimeter cubed, which is the area of one cell, we would be able to fit 428 cells within the 100 centimeter cubed honeycomb. And here we're going to try to find three types of cells that could tessellate properly within that honeycomb. And like I said before, the equilateral triangle, the square, and the hexagons are the only ways to do so. So what I did here is that I tried to find the individual lengths of each shape. So what we see here is that for the triangle, I tried finding for the value of A, and value of A is one of the side lengths. And in this case, after substituting in the area of one cell and then doing some math, and after that, we found out that approximately the side length of one equilateral triangle with an area of 23.4 millimeters cubed is 7.35 millimeters. And we did the same, I did the same with the square, which came up to be 4.84 millimeters, and did the same with the hexagon, which came up to be 3 millimeters. And before we move on, we can also see now that essentially the honeycomb conjecture is being proved here as well, because all three shapes have the same amount of area. But if you notice, when you add up the perimeter of each of these shapes, you see that the triangle overall has a perimeter of 22.05 millimeters as you multiply 7.35 by 3 because it has three sides. So the triangle would have a perimeter of 22.05 millimeters. The square would also have a perimeter of 19.36 millimeters, and the hexagon would have the least amount with 18.00 millimeters, which proves, again, the honeycomb conjecture, which is that the hexagon would have the least amount of perimeter with the same amount of area. So now we can move on by proving the overall perimeter of the application example. And so what I did here was that for the triangles, there would be 428 triangles overall because we determined before that there was 428 cells in one honeycomb that is 100 centimeters cubed. And because each side is shared between two triangles, we conclude that the equation would be 3 times 7.35, which is the side length of one triangle, multiplied by 214, which is the overall triangles divided by 2, because each side is shared between two triangles. And overall, that would mean that the perimeter is 47.2 centimeters. And we did the same with all the other two tessellations as well. And what we get is that the perimeter of the square tessellation is 41.4 centimeters, and the tessellation perimeter of the hexagonal tessellation is 38.5 centimeters. So why is this important? It's because that nature likes to be the most efficient whenever possible. So in this case, each cell in the honeycomb offers a certain volume, which is the thickness of the comb multiplied by the depth of the cell. The cells are made out of beeswax, which is a very high energy substance made by young bees, and young bees often die, creating only millimeters of beeswax. So it's really important for the bee colony to be really efficient with their usage of beeswax. They use a lot of nectar to get that energy, which is why it is expensive in quotations for them to make. So by applying the hexagonal shaped cells, they're essentially applying the theory of honeycomb conjecture, as the hexagon will compact more area, yet have a smaller perimeter than triangular or square cells. As a result, it allows the bees to efficiently create their structurally safe homes without having unnecessary amounts of space, and which allows for them to spend the efficient amount of energy or resources. So let's bring it all
Sorry,
together.
I hate to stop you, but your screen stopped sharing. Can you put your slides back up for us, please?
Sorry.
Oh, no worries. That's all good.
Is it working now?
Yeah, that's perfect. Thanks so much.
Where did I stop? Sorry.
I am not sure, but I think you can keep going.
Okay, so basically overall, I'll just re-summarize this, is that the honeycomb, they use hexagonal shapes because it's more compact and it takes less perimeter, so it's less expensive in quotations for the bees to make. So it allows them to keep their resources and use them efficiently. So now we can bring it all together and why hexagons are amazing. So the first point is that the hexagons are only one of the only shapes to tessellate properly without having any empty gaps in between, alongside the triangles and squares. And this is important because empty squares can have structural weaknesses because they're loosely held together. Regular hexagons are the shapes with the most area but with the least amount of perimeter, which we proved through the honeycomb conjecture. This allows for the highest packing efficiency, which we talked about with the honeycombs, and it minimizes the amount of material and labor needed for a given area, which nature really loves to do because it tries to be the most efficient with the resources it has. Also, the hexagons are consisted of 120-degree angles. This is important because when we put three hexagons all together, which we can see at the bottom, it makes a 360-degree area, a 360-degree angle, which is a circular point. And so when we have it in an arch type of position, it allows to be best at distributing stress and load in a structure. And also, a hexagon is the best fit for curved surfaces due to what I said before, and it is also the closest regular polygon to a circle that can tessellate due to these same reasons. So, hexagons in other areas, and what might be other examples of these phenomenons? A raft of bubbles floating on a liquid form hexagon-like shapes when the bubbles are blown all together and start adjoining each other. Although some bubbles may have 5 or 7 sides, most have actually 6 sides and have internal angles close to 120 degrees. Surface tension, and it's explained by surface tension. Surface tension is the property of a surface of a liquid that allows it to resist an external force due to the strength of it holding it together or cohesion. Surface tension causes each bubble to have the least amount of surface area, and we know that the hexagon allows for compactness, which is why the bubbles arrange itself into hexagon shapes. What we also see is a compound eye of a dragonfly, where each of the lens is acting as an individual visual receptor, where each of the lens forms into shapes of hexagons. Each visual receptor is a shape of a hexagon, and each eye has 30,000 of them. And each of these lenses have a different function, ranging from UV detecting to detecting prey. And this allows the dragonfly to have eyesight ability above any of its competitors. The reason the dragonfly is able to do this is because of the high packing efficiency of the hexagon. And if the dragonfly didn't use the hexagons, either there would be less lenses that could fit in the eye, which would be bad for its ability to look and see and be above its competitors, or the eyes would have to be bigger, which is not good for the anatomy of a dragonfly because dragonflies are small. We can also see industries using properties of hexagon. A majority of pencils are used in a hexagonal shape. The hexagon shape enables better, efficient packing when they're packaged in boxes. This shape allows for manufacturers to pack in more pencils per volume than any other shape, and they become easy to store. Hexagons are also used in organic chemistry. When 6 carbon atoms are bonded together, the angle is 120 degrees, which is the interior angle of the regular hexagon. The 6 bonded carbon form the perfect hexagon, and as we said before, hexagons 120 degrees are really balanced, and as a result, it forms the benzene ring. And there's even hexagons in space. Though this is a cloud pattern in Saturn's North Pole, scientists are still trying to figure out the reason behind this phenomenon, but it's still pretty cool to see how hexagons are far out there. And so this was a quote by Borg Louis Borg, and his quote was, The universe is composed of an indefinite and perhaps an infinite number of hexagonal galleries. And it's cool because he was not a mathematician, but a story writer. And in his short story, The Library of the Babel, he described his library to be hexagons and to evoke the sense of balance and perfection, which is pretty cool to see how hexagons aren't only applied in math, but in literature. And thank you, and I hope you learned something new.